I do that. Now I do that. Do and try to
And this is your oh. 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 Hello guys, you're welcome to God Academy. So we have applied electricity tutorials and we're going to solve some problems in applied electricity so that you understand it and prepare accordingly for your mid-semester exams. Okay. Hello guys, you're welcome to God Academy. So we have applied electricity tutorials and we're going to solve some problems in applied electricity so that you understand it and prepare accordingly for your first semester exams. Okay. Okay, so let's go straight solving our problems. And so for the first problem, our first problem, we are going to have, I have this circuit diagram I'm going to draw so that we solve. So I have this, then this here, and I have this. So this is a simple circuit, and we are going to find the respective variable, right? So this is 7 amperes, this is 5 amperes, this is 3 amps, this is 6 amps, this is 2 amps, right? So this is I, and the problem says find I. So you have to find the value of the current labeled I here. So that's the first problem you're going to look at. So this is a simple KCL or Kirchhoff current law problem, which you're supposed to find an unknown current given two separate network junctions, or what you call a node, right? So you can clearly see that we have one node here, we have another node here, right? So you have to analyze the current flowing through and arriving or leaving the junctions to solve for the value of I. So the first thing that you do whenever you get such problems is you go straight to the point and you find where is I coming from. That's the question that you should ask yourself. So the first thing is, where is I coming from? So you trace the path of I, right? And you realize that I is coming from this junction, right? So if I is coming from this junction, then you apply your first KCL here. So our first KCL, let me label this junction A and this junction B, okay? So first KCL at junction A. So at junction A, what do you see? You realize that within this node, we have 4 different branches. We have first branch, second branch, third branch, then this is our fourth branch, right? So for the fourth branch, we don't have any value. So let me use it. So we realize that 5 amperes is entering the node, 7 amps is leaving, and I is leaving. Remember, KCL says that current leaving should be equal to current entering the node, right? So therefore, we realize that there should be another current. I mean, it's a 4 branches. It's a 4 branch junction, right? So 1, 2, 3, 4. So you label the current which is arriving here. So looking at the junction here, you can label it any way. So depending on your label will determine the direction. Okay, so you assume that there is a current coming from this side. Okay, so now we have 1, 2, 3, 4 different currents. Okay, so upon analysis, you see that 5 amps is arriving. This current, which I can label as IA, okay, so IA is also arriving, I is leaving, 7 amperes is what leaving. So sum of current leaving should be equal to sum of current arriving. So at junction A, what are the sum of currents leaving the junction? So we have 7 amps, 7, right, plus I, which is also leaving, right? Then as well as the currents arriving, we have IA and what, 5 amps, right? So this should be equal to IA arriving plus the 5 amps. So this is the first step which you are doing. So it's 5 amps, so let me remove the A. So now this is what you have. Our interest is in finding the value of the current I, okay, not IA. But before you can find I, we need IA before you can find I. You put this down as equation 1. then we move forward and we go to where IA is coming from, because we need IA before we proceed. You realize that IA is coming from this junction here. So you have this junction, you ask yourself, now KCL at junction B. So at junction B, what you can see clearly is that we have 3 arms leaving, we have 6 arms entering, we have 2 arms entering. So this one IA is also leaving. So we apply the same thing here. So sum of currents leaving is equal to sum of currents arriving. So for the junction B here, for the currents arriving and leaving, we have IA. So I write my IA simply. Then I also have current leaving. I also have 3 amps, right? And this should be equal to sum of current arriving. And sum of current arriving, it's not making noise. What did you do? So it should be equal to sum of current arriving. So sum of current arriving, we have 2 amps, right, plus 6. So from this side, I can find the value of IA. So I'll say that IA plus 3 is equal to 8, right? Therefore, IA is equal to 5 amps. So this has given us the value of what? IA. So I have the value of IA from this end, right? Then from this end, I can find the value of I simply by substituting the value for IA. So let me write from equation 1. So from equation 1, we can say that 7 plus my I here is still maintained is equal to my IA, which is now 5 plus 5, right? So I'll say that 7 plus I is equal to 10. Therefore, I is equal to 10 minus 7, which is 3 amps. Therefore, the value of I from this network is 3. I'm not live tutorial. I'm live tutorial. They're making me. So the answer is 3 amps, and that is for the first question. The answer is 3 amps, and that is for the first question. So we proceed to solve our second problem. So let's solve an interesting problem here. Question 2. Find the value of current I in the circuit below. So this is the circuit. So I have 10 amps entering here. I have my 2 ohm resistor here. I have 1 ohm resistor here. Then I have 4 ohms resistor here. Okay, so this is the current I which is leaving, and that is what you've been asked to find. So to find the current I here, we need to analyze the circuit very well, right? So our goal is find the value of the current I in the circuit below. Find the value of the current I in the circuit below. So within this circuit, where is I? This is I. We can locate I here. But how do you think about this problem? The source here we have is a current source. The current source is arriving at this junction. Upon arriving at this junction, it can sense this junction, as well as sense this junction. But we want the current through one particular branch. So here we call it current division problem, okay? Because the total current coming must divide. So we want to find a fraction of the total current that will pass through this 1 ohm resistor, and that is what we are interested, okay? So now let's see, how do I use current division to find the current through this? Current division is an inverse relationship, okay? So that if you have, and always please take note, current division deals with only 2 resistors at a time. Whenever you are dealing with current division, we use two resistors at a time. So here, since we have three different branches, for us to successfully apply current division, the first thing that you're supposed to do is to make sure that you have compressed these three into what? Two. How do you do that? You can only do that by simplifying or finding the effective resistance of the other two, which is not involving the current I. Okay, so here the 2 ohm and the 4 ohm should be our target to merge. But you ask yourself, are they in series or in parallel? There is a node here, there is a node here, meaning that, and there's even another node. They can't be in series. But let's traverse through their paths. We realize that there is no other element which is within their path. Therefore, we can say that 2 ohms is parallel to 4 ohms, right? Therefore, we can find the total resistance as 2 times 4 over 2 plus 4. This gives us 8 over 6, and that is what? 4 over 3 amps. Oh, sorry, 4 over 3 ohms. So therefore, you redraw our circuit, and when you redraw our circuit this time, you have 1 and 2. Sorry, you have 1, then 2. So we have our 10 amps here. Then we have our effective resistance give us 4 over 3 ohms, right? 4 over 3 ohms. Then this one is giving us, we have our 1 ohm here, and the 1 ohm there is a current I which we are interested in finding. Okay, so once you have this expression here, once you have this here, we can apply our current division successfully, right? So our current division here is simply, you remember that current division, whenever you want to find a current through a particular resistor using a current division, you rather take this resistance over their sum times the total current. Okay, so here I'll have my current I to be equal to the opposite one. It's not a resistor current, the current, so you take the opposite one, so it's going to be 4 over 3 all over 4 over 3 plus our current, so our resistor here which is 1, times the total current which is 10, right? So at this point you're going to have I is equal to 4 out of 3 all over 3 times 1 plus 4, which is what? 7 out of 3 times 10. Okay, so simplifying this, 3 will cancel 3, then we have 4 out of 7 times 10, right? So you simply punch this one into the calculator to see what you get. So 4 out of 7 times 10. So 4 out of 7 4 out of 7. So that's giving 5.714, okay, amps. But please take note of something here. You realize that the direction of the current here is against the flow. Sometimes in applied electricity, you solve and get your answer right, but you may be wrong, because if you don't pay attention to details, you realize that the current is rather moving up, and the major current is coming here. Therefore, to find the current I, it will be negative of what you've gotten. Okay, so I is simply equal to negative 5.714. Take note of that, and that makes our answer. This is the answer. Okay, so if you don't write negative 5.714 amps, you are wrong. The current is supposed to divide and come down, but you can see clearly that there is this current coming up. Therefore, it makes it negative. So let's go to our third problem, our third question. Okay, so the question number 4, question number 3, right? So our third question. So our third question, we are going to have this here. Right. Okay, so the question number 4. So this is our fourth question. So and our third question. So I have my total voltage here, which is um 10 volts. I have 4 volts. Then I have 2 ohm resistor. I have R. And the question is find R and V. We should find the value of R as well as V. How do you find the value of R and how do you find the value of V? This is a simple circuit, right? So it may look very easy, but it takes, understanding of concept before you can solve this problem. So I have 10 volts, which is my total voltage in this circuit. Okay, I have an unknown resistance here, R. I have the voltage across 2 ohm to be V, and I have the voltage across 4 ohm to be V. How do I solve this problem easily? Now, to solve this problem, you understand by concept that in any electrical network, the total voltage drops within the circuit is equal to the total potential difference or the total voltage in the circuit. Okay, so without even solving anything, we realize that 10 should be equal to 4 volts plus the voltage across 2 ohm resistor, which is what? V. Therefore, 10 should be equal to 4 plus V, and we can say that V is equal to 6 volts. So therefore, this V now becomes what? 6 volts. Okay, this is how we find it. As simple as that. So always make sure that if you are given an electrical network, don't be in rush to apply the KCL and the KVL. Make sure you analyze maybe what's the voltage across here. Can you just use analysis? Okay, so here, since we know that the voltage across 2 ohm is what? 6, what do? We need to find the value of R. How do I know the value of R? How do I know the value of R? Remember that in any series connection of 2 resistors, the current flowing through them should be the same. So the current flowing through this 10 volts will come and pass through the R, and as well as come and pass through this 2 ohm resistor here. Okay, now once the same current is passing through, meaning that if I'm able to determine the value of current passing through, I can use the Ohm's law to find the value of the R here. As simple as that. I have my V to be equal to 6. Therefore, I is equal to V over R, right? Therefore, I'm having 6 over my R is equal to 2, giving me 3 amps as the current. If the current coming from here is 3 amperes, the same current will flow through this. Therefore, to find R, I don't know R, my V is equal to 4 volts from this side, and I have my current I to be equal to 3. Therefore, to find R is simply V over what? I. Is that not it? Because it's V is equal to IR. So I want I, so I'll make R the subject, I'll get V over I. And my V is 4 over my I is 3. Therefore, the value of the resistance is what? 4 over 3 ohms. As simple as that, right? As simple as that. Since you have the current, that is exactly how we approach this problem. Okay, so this is for our third question. Let's quickly do for our fourth question. Our question number 4. Question number 4. So for question number 4, we are going to have simplification of resistance of a circuit. Okay, so let's see. A naught, then I'll have this, then I'll have B, right? Then I'll have this, I'll have this, right? Then I'll have this, I'll have this, like this. So I have 6 ohm here, I have 4 ohms here, 3 ohms, 4 ohms, 1 ohm, 3.3 ohm. we have to find the effective resistance across the A and B, the terminals A and B here. How do you find the effective resistance? We need to find the total resistance across these two terminals. Okay, please, whenever you are finding the effective resistance in any electrical network, don't be scared about the complexity with the arrangement of resistors. Just go by principles. By principle, we take two resistors at a time. Okay, and you should always start away from your source, away from your terminal, then you simplify close to the terminal. Okay, because of that, you come to the far end of the terminal. At the end of the terminal, I can see my first two resistors, which is 4 and 6 ohm, right? And 4 and 6 ohm here that you can see, you ask yourself, are they in series or they are in parallel? There is a node here, there is a node here. That makes it not in series. But let's see if it will be in parallel. You need to traverse through their paths like this. And once you traverse through their paths, you shouldn't meet any other element aside these two resistors, okay? And that makes it what? Parallel, right? So we can say that 4 ohm is indeed parallel to 6 ohm. Then we simplify this. 4 by 6 over 4 plus 6, right? This gives 24 over 10, which is 2.4 ohms. So I can then remove these two branches and make it one branch because I've simplified the resistance. So you can see that this will go away, then to be left with this, right? So redrawing my circuit, I'm going to simply have something like this. Please try and redraw your circuit anytime you are simplifying any circuit. Okay, it will help you so that you get it right. If you don't and you try to be using your eyes, you may get it wrong depending on the complexity. So at this point, these two becomes one like this. So here I'll have 6 and 4 collapses to 2.4 ohm. I'll have my 3 ohm here. I'll have my 4 ohms here, 3.3 ohms and 1 ohm. At this point, my last two resistors are what you see here, 3 ohm and 2.4, clearly in series because the same current will flow through. I will collapse it without even redrawing by removing this because it's 3 ohms. Then I'll have my circuit completed. Then I'll change the value for my 2.4. Then that will become 5.4 ohms. Okay, that become 5.4 ohms. 5.4 ohms. So now look at where we have reached now. And as I said, we still work away from the terminals, away from the source, so we get close to the terminals. Okay, so here we are going to consider 4 ohm and 5.4 ohm. They are in parallel. 4 ohm is in parallel with 5.4 ohms, right? So this gives 4 times 5.4 over 4 plus 5.4, right? So you punch this on the calculator. So 4 times 5.4 over 4 plus 5.4, and that is 108, or in decimal form 2 points, let me make it 108 over 47. Please, one thing to note, whenever you are simplifying resistance, don't be tempted to leave your answer in decimals. Make sure you are done before you press it, otherwise you may miss decimals and the answers in the options may be very close, which you'll be confused, right? So we redraw our circuit once again, and we are going to have A and B, where my terminal is like this. I have this coming down here. Since I've collapsed this and this, right, I'll have only one coming like this into my terminal. So here I have 108 over 47 ohms. I have my 1 ohm, then I have what, 3.3 ohm. You can clearly see that the last two resistors are this and this, right? So you add them, it's in series, right? So 1 plus 108 over 47, what is that? You punch that, so that is 155 over 47 ohms. So you simply clean this one, then you write accordingly 155 over 47 whilst cleaning this one too. So I'll have this cleaned like this. So at this point I'm left with only 2 resistors, right? Please, the bent resistor here is not bent, as in you can redraw it and make it straight. It's just something to trick you, okay? So you can make it something like this, So this becomes our B, this is our A. Then we have our label 3.3 ohms. We have 155 over 47 ohms, right? Now you can see that they are in parallel clearly. So you simply state that 3.3 ohms is parallel to 155 over 47 ohm, right? So 3.3 times 155 over 47 all over 3.3 plus 155 over 47. What are you getting? So this is a long one. 3.3 times 155 over 47. 3.3 plus 155 over 47. 1.6. So I have 1.6495, right, amps. Depending on the number of decimal places you have to leave it, then you leave it like that, right? So this is approximately 1.65 ohms, right? 1.65 ohms. 1.65 ohms. Okay, that is for question number 4, right? Yeah, so let's go to question number 5. Question number 5 here. Okay. Okay, so question number 5. I have this circuit here. Then this goes here. So I have this to be 2 ohms, 7 volts. This is 5 ohms. Then I have this to be 4 ohms. We have to find the current. Sorry. Let me check. Okay, so we have to find the current here, I. Okay, so we have to find the current I of this circuit. So how do we find the current I? So find the current I of this circuit. To find the current I of this circuit, let's analyze this circuit well. Anytime you are given an electrical network for you to analyze, please make sure you identify your power source, then follow through where the current is passing. There is 7 volts here. 7 volts will produce current, and that current will pass through at 5 ohm, right? Upon reaching this junction, there are how many branches? There is one branch, branch 2, then there is a third branch, right? So branch 1, branch 2, branch 3. These are the 3 different branches. Please, current always seeks to pass where there is minimum or almost no resistance, right? Picture current as a flow of water. So if current is flowing, right, upon reaching here at this junction, it will quickly send this as an obstacle. Please, you can see the 2 ohm is here, but the 2 ohm can be here. I mean, don't picture it like it's far away. The current will not flow here. It's on this branch. So in reality, the 2 ohm is actually felt right here. Okay, the 4 ohm can be felt right here, but there is another quickest branch here. Therefore, the current will pass here. This is what we call a short circuit. Okay, a short circuit. So this branch here actually has 0 resistance. So the current will move here and come back. So this is what we call something effective circuit. Okay, writing the effective circuit. Effective circuit is mostly when you want to remove all short-circuited resistors to get the effective resistors. Okay, so in order for us to find the current I, we need to know the effective resistors which will be in play, which will be working. Now, since the current will just skip this resistor and this resistor, we can confidently say that the 2 ohm resistor and the 4 ohm resistor have been short-circuited. So the effective circuit for this is simply going to be having this here, this, this to this. So this and this are not active, okay, because they are not having any role to play. Here is 7 volts and this is 5 ohms, and I have my current I, right? So I have I to be equal to, this is 7, right? To find I using Ohm's law, V over R, right? So my V is 7, my R is what, 5. What's the answer? 5 goes here 1, leaving 2, so zero point 0.4 amps. And that is our answer. This is to introduce you to the concept of short circuits and how to identify short circuits. Okay, so this is the answer for our fifth question. So before our next question, a quick note before we continue. So GAD Academy only started producing videos actively last year, and already about 20,000 students have watched us. Yet we are still under 1K subscribers. If you are finding value here, please hit the subscribe button and help us amplify this work. I really appreciate it. So we can proceed to our sixth question, right? Okay, so question number 6. Right. Now let's do something here. I have this nice circuit here. Like this. I have this circuit here. Like this. Then I have this here. So this here is 6 volts, 12 ohms. This is 8 ohms, 10 ohms, 15 ohms, 5 ohms, then 4 volts. So there's a problem that you have at hand. It says that find the current in the 10 ohm resistor, right, using both Thevenin and Norton's theorem. Okay, so we are supposed to use both Thevenin and Norton's theorem to find the current through our 10 ohm resistor in this branch. And here we are solving 2 different problems in one. Okay, in the midsem, for those who be doing written, this problem will come as written, but those who be doing OBJ, you have it in different section. The options will say number 1, find your RN and IN. Find your IN, right? Number 2, find your RN. Number 3, what is the answer of I? So always any Norton or Thevenin's question within the OBJ comes in 3 different questions, like 3 in 1. Okay, it becomes a preamble. So this question right here is like 6 questions for OBJ, and it's also like 2 questions for those who be doing written. Okay, so please pay close attention. And in the applied, you are working against time. You are working against time. You are not just working. Okay, you are working against time. So you have been given this network for you to find a current through just this 10 ohm resistor, and you need to use 2 different methods. So first thing to do, let's check the Thevenin's method. Okay, what is Thevenin's theorem? Now Thevenin identifies that whenever you have a very complicated electrical network, and very complicated indeed, with so many resistors, applying the KCL and the KVL to find those parameters will become very difficult. And in view of that, you need to find a way we can find current in a particular resistor without having to destroy or without having to find unnecessary current anywhere. That is why Thevenin and Norton came in with their theorem, so that we just remove that resistor and do 1 or 2 things, right? So now let's talk about Thevenin now, then we understand it. So Thevenin, okay, so we have Thevenin. So what is Thevenin saying? Thevenin is saying that whenever you have a resistor in an electrical network and you want to find a current through that particular resistor, the first thing to do is take away that resistor. And when you take it away, you create an open circuit. So see something here. You redraw the circuit here. Sorry. So I have this. Then this will go here. At this point, I'll remove it and I'll create my branch here. So this one is also going to be removed. I'll have this here. Then I have this here. I have this. So our interest is only the resistor you want to find a current through, okay? This 4 volts. So now we've been able to remove it, and what Thevenin says is once you remove your resistor, the next thing is you introduce an open circuit voltage VTH. It's a special voltage VTH, okay? And assign it a direction. So we assume that there is a voltage source here. It's just an assumption, okay? A voltage source here, which is having a direction pointing this way. Remember, this voltage source is pointing up. This is pointing up, right? So whenever you have a voltage source, where is the direction your current is flowing? You need to know. It will help us find our current, or it will help us whenever you are taking a loop. You know the right sense you have to pass, right? Now we have 15 ohm resistor here. We have 8 ohm resistor. Please, whenever you want to find the VTH, okay, some students will wonder, please go straight to the point, to the first equation carrying the VTH, okay? So now let's come to the branch where the section. So here I can say that I have A, B, C, right? 3 different loops clearly that I can see. So one box, second box, third box, and VTH is within the B. So for me to find an equation involve VTH, I'll just take a loop here, right? So what do? I know that for me to take a loop here, I need the current passing through this, a current passing through this. But please see something. Whenever you are about to solve this circuit, go straight to your current sources, okay? Within my current, my voltage source here, or your power source, I have 4 volts. 4 volts will surely produce a current, I. And remember that the current I will come and pass through this 5 ohm resistor, and upon reaching here, there is an open circuit. Please, current cannot pass through here. Whenever you are solving VTH, current cannot pass through it. So that current will bend down and come and pass here as I1. I don't know if you get it. So the same I1 that we produce here will come and pass down here as I1. Then we come to this circuit here. You realize that it will produce a current I2, right? The I2 will pass through the 12 ohms. Upon reaching this junction, cannot move across because this space has been opened, and it will only come down as I2. So just picture I2 coming from 6, I1 coming from 4. Now we can go ahead and find our equation involving VTH. So we simply say that taking this sense, look at the loop that I've taken like this, right? So my VTH is simply equal to 15, in the same sense, 15 multiplying I1, right, plus, but since it is moving against this sense, it becomes what? Negative I2 multiplying 8 ohms, right? So my VTH simply becomes 15 I1. So it becomes 15 I1 minus 8 I2, my equation 1, okay? My equation 1, like this. So this is my equation 1. VTH is equal to 15 I1 minus 8 I2. Now, since you have found the equation for VTH, what do we need to get a VTH? We need I1, we need I2. How do I find I1? How do I find I2? Looking at this branch, I have everything I need. I can find my I1 here, I can find my I2 here. So I move straight to this side. I'll take a loop like this, since I always choose to follow the right sense of what? My current, okay, my voltage source. It helps a lot to avoid negatives, right? So move always in a direction like this. So my 4 volts will be equal to what? A current passing through here is I1, a current passing through, so I'll have 5 I1. The same I1 will come and pass through 15 plus 15 I1, okay? And that is all. It will come back. So I'll say that 20 I1 is equal to 4. I1 is equal to what? I1 is simply equal to 4 over 20, which is 1 over 5 amps. Let's come here. I2 produced I2, 6 volts produced I2. It passed through 12 and came down to pass through 8. So it's the same loop that we are taking. Follow the sense like this, like that. So I'm going to have 6 to be equal to 12 plus 8 is 20. Let me make it systematic. So 12i2 plus 8i2, right? They are moving the same sense. Therefore, I have 20i2 is equal to 6. Therefore, my i2 is simply equal to 6 out of 20. Is that not it? Which is equal to 3 out of 10. Then after getting these values, I simply come to my VTH and find it. As simple as that. So my VTH simply becomes 15 multiplying the I1 value I had, which is 1 over 5, minus 8. I2 value I had is 3 over 10. As simple as that. 5 goes into this of 1 and goes here 3, minus 2 goes here 5, 2 goes here 4. That is 12 over 5, right? 12 over 5. So since we have 12 over 5, we are going to have so what are we getting here? We have 3 minus 12 over 5. So please punch into your calculator to get a fraction. So that is 3 over 5, okay? So our VTH, please don't believe in decimal place, but 3 over 5 is 0.6, which is finite, or which is terminating, so it's okay, okay? So we're going to have 3 over 5 V, and that is all for VTH. Remember, we are not done, even with Thevenin. The next thing you have to do is to find out what? Our RTH, okay? Thevenin says you should find our RTH. With our RTH, I'll draw my circuits. And remember, whenever you want to find your RTH, you close this. This becomes a short circuit. Remove all the voltage sources, make them short circuit, okay? So we get a straight short circuit here. You get this, then we get this. Then within our open circuit, we come to get our RTH functioning here, okay, as a resistor. Then we come here like this. This comes here and like this. So here I have my 6 volts became a short circuit. I have my 12 ohms here. I have my 8 ohm. I have my RTH. I have my 15 ohm. I have my 5 ohm. Now we have to find RTH simply by applying the principles of finding effective resistance of a circuit. So here I'm going to have 8 times 12. See, at this point you can see this and this are in parallel, as simple as that. So 12 ohm is parallel to 8 ohm. That is 12 times 8 over 12 plus 8, right? This is 96 over 20, which is 48 over 10. That is 4.8, right? So I can collapse these two and give me 4.8, right? So see, remove forward. I simply get this. Then I have my open circuit here, but these two have been collapsed, so I have something like this. So they become 4.8 ohms. This is my RTH, right? This is my 5 ohm, and this is my 15 ohm. At this point, you can see something clearly that on my left side, away from our terminals, 5 and 15 are also in parallel. So 5 ohm is parallel to 15 ohm. I'll simply get 5 times 15 over 5 plus what 15. This is 75 over 20, right? So 5 goes here 15, 5 goes here 4. So what is 15 out of 4? You can leave it like that, and let's redraw our circuit. So redrawing our final circuit, we are simply going to get our circuit to be this way. So I'll have this collapse as 1 to my RTH, which is in between the terminal. This goes here to 4.8, right? Like this. So I have my 4.8 ohm, and I have my 15 out of 4 ohm. Okay, so here you can see that everything is in series. Therefore, my RTH is equal to 15 out of 4 plus 4.8. Okay. So 15 out of 4 which is 171. Okay, it is 171 over 20, and that is our RTH. So now we have our VTH to be equal to 3 over 5 volts. Our RTH is equal to 171 over 20 ohms. Please, Thevenin's circuit. Let's draw Thevenin's circuit. Thevenin's circuit says that we have a particular electrical network with our voltage source called Thevenin's voltage in series with our resistance or Thevenin's resistance. In series with this particular resistor, we want to find the current through. Exactly. So within this circuit, we will replace it with the variables we found. Like this, right? So I'll have my VTH to be 3 over 5 volts. My RTH will be 171 over 20 ohms. Then this is 10 ohm because we found the current through the 10 ohm. That's what we want to find. Okay. So here you can see that it's a simple circuit, right? So to find the currents, which we need I. Okay. So I is simply equal to V over the total resistance, which is the sum of this and this. So I is always equal to VTH over R plus RTH. Okay. As simple as that. I have my VTH to be 0.6, which is 2 over 5, all over my R, which is 10, plus this is 171 over 20, okay, and that is 8.55. So what's the answer? 0.6 over 10 plus 8.55, and that is giving 0.032 amps. Okay, and that is our answer by Thevenin's approach or Thevenin's theorem. Okay, so we still press on to find our Norton. So we are solving the same question using Norton, please. So let me clear the Thevenin side and solve